term. So visiting us from the University of Swansea, we have Edwin Beggs, who will talk about
star structures, complex structures, line inner products and line bundles and stuff.
Perfect. Okay, please.
Okay. Well, I want to talk about differential calculi one problem with the differential calculus that you might want to use on, say, the integers is if we have a differential structure on the integers, which is just given by a graph like that. So this would be generator E plus with which just jumps one along the integers. Then if this will not be a star calculus, because to have a star calculus, you really need to have something going in the other direction. So I'm partly interested in what you can do if you only have half of this. What can you still say about star structures, even if you only have half of this? But I'm also interested in this doubling up construction. And so I guess my story really begins with another example, which is the braided complex plane. Have I got that the right way around? Oh, this will be up to a plus or a minus in there. I can't remember which one it is. Right. So the problem with the calculus on the braided complex plane, as normally given, is it's not a star calculus. So what I want to do is I want to look at a particular origin of the braided complex plane and show you, well, its origins in a braided category, and then explain why we naturally get two calculi, which is pretty much like doubling up these arrows. So you have to add both of these two calculi, which are themselves perfect good calculi, but you have to add them together in order to get a star structure. So I want to talk about a braided monoidal category. So I guess I need to say a little bit about what a monoidal category is. So monoidal category will have objects and tensor product operation between objects. The most popular ones to look at would be the bialgebra, the bimodules over an algebra A, and in which case we'd have a tensor product over A operation. And the one I'm going to be more concerned with is if H is a Hopf algebra, I'm going to take its comodules. So the objects of this category are going to be co-representations of a Hopf algebra H, and I'll write let's have right co-representations, which I'll write like this. So V is an element of V, then V naught will be an element of V, and V1 will then be an element of H. And as this is a Hopf algebra, I can take a tensor product of two co-representations. Just by multiplying the Hopf algebra valued terms. So this is going to give me a monoidal category as long as I use operations between co-representations, which are just maps of co-representations. Now I'm going to use a diagrammatic notation for quite a lot of this. So if I've got V tensor W, I'll write that as just two vertical lines, and you can imagine that that's a tensor product between them. And an operation between these, like an operation T, which swaps these around, swaps these around. I will just write like this, but I want to consider a particular sort of Hopf algebra. A co-quasi-triangular Hopf algebra. And the important thing is that we need an R matrix. Well, it's a linear map from H tensor H to our field of the complex numbers, obeying various properties of which okay, that's a slightly optional star property, which I'll come back to in a moment. But what this R matrix gives us is a preferred co-module map from a co-representation V tensor W, which swaps the order. So let's write that in here. And in this monoidal category, I'm going to write this, have a flick through here to try and maintain some remote bit of consistency. So here VW, that goes to WV, and this is the braiding operation on VW. And the properties which I haven't written down about a co-quasi-triangular structure basically tell you that this behaves as though it was just pieces of string. You can pull crossings through other crossings as long as this string goes over that string and you keep everything consistent. It all works. Okay, now what I want to look at now is the braided symmetric product construction. So let's take V, which is a co-representation, and what I want to do is, well, just take the tensor product of V. Well, that's easy, you just write out however many things, but I want to quotient it by something which makes it symmetric. And it turns out that as long as I keep all of these braid crossings going the same way, in other words, I just have psis and I don't sneak in any psi inverses, that a lot of the things from just a theory of permutations can be written out. And if we take a little bit of care, well, let's define firstly the operations on, well, let's take 4 copies of V, and now I want to look at this braided integer on here. So first thing I do is I do crossing of the first 2 things over, then I take a crossing of this like that, and then I cross all of these things. Now, using this, I can define braided factorial operations. Okay, yes, I want that to, right, yes, curve first. So factorial operation ought to have, if we take this braided integer up here, now we then compose it with, just being slightly careful with this so that is now the identity, and now we've got the braided integer n minus 1 here. So all of this is doing is it's a symmetrization operation. And these things just work, and I'm not going to say much more about them apart from the fact that they work. But V plus of V, which is the braided symmetric algebra on V, is a tensor algebra on V divided by the appropriate dimensional kernel of the braided factorial. Now, I do really need to mention what this bottom line is, because we're going to come back to it. Because this bottom line, we will need to be reasonably well behaved. You can very well imagine that if these braided factorials are just some random linear maps, that their kernels are going to be 0, and we'll have the whole tensor product algebra, which is not necessarily what we want. Okay, well, so much for a braided category. I now need to say a bit about how to put a star structure on these things. Now, for lots of definitions in mathematics, you can be quite careless about the distinction between modules and conjugate modules. So if I have a module E, which is over a bimodule over a star algebra A, then the conjugate module has got elements little e bar, where little e is in capital E, and you take the star of, well, the action is given by taking the star of the algebra element you're acting by and placing it on the other side. And likewise for the other way around. Now, for a co-module, V bar has got elements little v bar, where little v is in capital V. And, well, I've told you what the coaction on V is here. Now, what is the coaction on V bar? Well, it is where I now need to have a star structure. Well, this should be some sort of star structure on a Hopf algebra. And it's probably safest to say it is actually a full Hopf star algebra. Otherwise, we'll get some slightly weird things happening. But that's certainly the case that we're going to get. Now, very often, people, well, for example, in the definition of a Hilbert C-star module, will just write lots of special cases to get around the fact that there really ought to be a conjugate module in the definition of a Hilbert C-star module, but you have these things where sort of algebra elements hop around and so on. To do this, we to do a braided category, we really can't do that. We have to really recognize the fact that there are conjugate modules. Otherwise, the bookkeeping gets unbelievably horrible. So in that case, we have the standard structure of a bar category. So basically, bar is a functor from our category to itself, and it is related to the tensor product by the following operations, which you can basically remember as star reverses order. So for what it's worth, that's a usually written capital epsilon. Oh, sorry, I should have said H. So, and the fact that this is a morphism in the category just comes down to the fact that you have a Hofstar algebra. And now this thing which I wrote down here is, well, that's a reality condition for a braiding. So since bar is a functor on the category, well, I can apply it to any morphism. So let's V tensor W. Okay, let's so in particular, I can apply it underneath the bar just by applying it, well, to whatever's written underneath the bar, literally. And now I can use an epsilon on that to get that going to V bar tensor W bar. I can use epsilon on this one to get to W bar tensor V bar. Now, this will have a braiding itself. That goes to V bar. Well, basically, that goes to that, if I'm correct. And that, and this will work because of this reality condition here. Another thing we could have had for another choice of, well, anti-real condition is this could have been a braiding inverse. But, so basically these bars are just bookkeeping devices. They're there to make things a lot better, though it doesn't look like that at the moment, simply because the examples which often occur are so simple it doesn't much matter. But well, basically, for one thing, you in one of these braided categories, you do not have a star operation. Why? Well, because your maps between modules, well, a co-module map is first of all a linear map, and a star operation is not a linear map, it's anti-linear. So in order to put the star operation into the category, we need, well, I'll define an open star, which goes from V to its conjugate. So open star of V is V star bar. So that will say that this is a star object in the category if there's a morphism of this form in the category. And that now, taking the conjugate here just means that this map is linear and therefore that it is a candidate, well, hopefully going to be a co-module map or whatever.
Yeah, just a quick question. So we know that to the psi here corresponds the R form, right? So what would correspond to the epsilon? Is it just like R composition with the star, or is
no,
there some?
In this case, and in an awful lot of cases, it's really very trivial. That's it.
So there's no R matrix that braids this?
No, none at all. And it basically you just work it out and it gives you a co-module map. And it gives a co-module map basically just because of the rules of being a star Hopf algebra.
Okay. Okay, maybe just a very quick question. So I don't see where you need the antipode. So is it really needed that you have a Hopf algebra, or would it be fine to work with a bialgebra?
The answer is I'm not sure at which stage this comes in. I mean, you certainly, well, for this braiding, you need a co-quasi-triangular Hopf algebra. And, but for, if you want to reverse sides of actions, you need the S's, but probably for at least some of this theory, if you keep all the actions on the same side, I think you can get away without S's, I think.
Exactly, because they're the antipode corresponds to the rigid monoidal category, right? So, okay, thanks.
Okay, so what I'm going to assume now is let's go back to this braided construction, and we're going to assume that V is a star object. So we've got a morphism like that. And if you do two of them, then it's just V goes to V bar bar. Now, need to make some more room. So I'm going to claim that with this reality condition on the braiding, which is it, that's just the braiding rather than its inverse there, that B plus is a star algebra. Now, again, I need to put all the operations into morphisms in the category, which means that I'm forced to use bars on them. So let's take B plus tensor B plus. And if I take open star tensor open star, I will get now from here, I can do a product and go to B plus. And then I can do an open star operation and to get to B plus bar. Oh, yes. Now, so I've then got this order reversing map here. And on here, I've got a product under the bar. So that's a definition of a star of a star algebra in this category. And it works. Now, the other thing is that, well, in fact, this is going to give a star Hopf algebra in this category. Now, what is the coproduct? Well, the coproduct is, well, what is it on V? This is just basically a symmetrized tensor algebra. So let's look at it. It's trivial on degree 0. On degree 1, I have an element of V, and I want to, this is just a divider, which is there. I can send it on that side, and then I'll add it to what happens when I send it on this side of this divider. If I have got two of these objects, I can well, basically, I send the two copies of V in order either to one side or to the other side. And really, this operation is would be, well, I've talked about these braided factorials. This is a braided binomial coefficient, because the braided factorial can be factored into a braided binomial operation, which shifts it as sort of r copies, r out of n copies on that side, r n minus r copies on this side, and then the factorial just permutes the n copies and the n minus r copies and so on. So anyway, there is a pictorial way of doing this, which makes a Hopf algebra where the co-unit is just going to be projection to the complex numbers, to getting rid of all of these. So I need to look at a particular example of this.
Which, and this is just the usual Hopf algebra structure on the Nichols-Voronovich.
Yeah, so this construction is so far all pretty historical. So as you said, we're doing it in Nichols algebra construction with the added stars. So before I forget, I should say that this is all joint work with Shan Majid on a paper which has just come out on the archive this morning. So don't ask me what its number is, I don't know. Okay, so I'd like to look at now the braided plane. So I'm going to take the Hopf algebra C cube SU11, which has got, well, it's just got the normal Hopf algebra structure as in SU2, apart from the fact that it's got a different star operation. So it's got A star is equal to D, and B star is equal to Q inverse C for Q real. Okay, so what I'd like to do is to take B, which is generated by, well, in 2 dimensions, generated by Z and W. And I'd like to take the co-product which is this, so Z, sorry, rather, coaction, so coaction on Z is Z tensor A plus W tensor C and so on and so on. And then do all of this construction, and it doesn't work. Or rather, it does work, but it doesn't give you anything interesting. It'll give you the entire tensor algebra. For reasons I mentioned earlier, I wanted to have this show you what this kernel that we were dividing out by on the tensor algebra is. And if you put a random matrix in there, it's, well, a random matrix will have non-zero determinant, no kernel. So we have to be a little bit more careful. So this is the symmetry that we really want, but we're not quite going to get it. So we'll do the next best thing. We're going to centrally extend it. Well, it's going to be quite a trivial central extension, really, that we're going to take this tensor product we're going to take an invertible element T, and where T is group-like, so co-product of T is just T tensor T. Invertible it needs to be a star algebra, so I'll tell you that T star is equal to T. Okay, in that case, where's the acutely alpha come in? Well, acutely alpha comes in because this is also going to be made quasi-triangular. Now, with a bit of luck, I might even be able to find the formula where I wrote this down. Okay, good. So the R matrix on T to the M, T to the N will be acutely alpha MN. So that's what this subscript is. It refers purely to the quasi-triangular structure. And I'm going to modify this coproduct by putting in a tensor T at the end. And so now we want to go through the construction, and what we want to do is to actually get something that looks the right dimensions for a braided plane. In other words, we want to have some sort of commutation relations between Z and W is going to be Q to the half times Z star or whatever. So for W, you might as well read Z star in here-ish. So what we have is literally a matrix that we're dividing this tensor algebra by. Well, we have to divide out by its kernel. And to do that, to have a non-trivial kernel that produces the right, anything vaguely like the right commutation relations in degree 2, you work it out and you get the alpha has to be equal to 3/2. So without the central extension, we're just not going to get a braided plane. It'll be far too big. I was practicing yesterday to get my board swiping technique. So just to give you a little bit about what this is, if you write down the braiding here, you will get QZ, well, and so basically the braiding is just giving you the relations in the algebra. Okay, now how to make a differential calculus in the braided case. So let's take yes, so V is two-dimensional, and it's got generators Z and W is just something like Q to the power of half Z star, which I'll translate into Z stars in a moment. It's just normally written like that. No, well, basically it's got the same sort of dimensions as it would have classically, just powers of of two commuting Z's and W's. So if I have B plus, then I can take the co-product, which takes me to B plus tensor B plus. Now I'm going to apply a map, which is just, this map is projection to the degree 1 part. So it's now going to take me to B tensor V. And that will be the identity. So I'm going to just remind myself which way this is. So this is the normal differential. This gives you the normal differential calculus on B plus, and I'm going to call it omega 0, 1. I guess I need to say a bit about complex notations. Okay. So for a complex differential calculus, so let's just take a differential calculus on C, and I could write Z equals X plus IY on C, but I'm not going to do that. I'm going to write everything in terms of Z and Z bar, which is X minus IY. So the differential calculus, which involves DZs, that is a differential calculus in its own right. I can just consider DZs and nothing else. And that I'm going to call omega 0, 1. Oh, no, I want that to be 1, 0. And if I just consider DZ bars, I'm going to call that omega 0, 1. So in general, on a complex manifold, if you have a complex coordinates, you can split any complex n form in just by counting how many DZs there are and how many DZ bars there are. And so omega PQ is the forms which have got P DZs and Q DZ bars in them. And this forms, well, it's an integrable complex structure. The first thing is that star swap Z and Z bar. So there is a star operation from this to omega QP. And in addition, the D operator just takes your line of DZs and DZ bars, and it does a partial derivative on the first thing. And that partial derivative will either hand you an additional DZ or an additional DZ bar. So the total is that omega PQ, if you apply the derivative to it, then if you get the bit which has got an extra DZ in it is going to be that, and that direct sum, the bit which gives you an additional DZ bar. And we'll split the D operator into curly D, which is just in the Z direction, and D bar, which is in the DZ bar direction. And that's basically an integrable complex structure. So D, the ordinary D, is split into curly D plus curly D bar. So this derivative here, the ordinary derivative, we're going to say that this is a D bar direction. And you imagine that if you took 3 copies of V coming in here. You send one copy of V over here and 2 copies of V going there. And your factorials do all the counting for you. And you would, in the classical case, just end up with the ordinary derivative. But there's another one that we can have. We could have B plus goes to, well, take the co-product again, B plus, B plus. We could take projection to the first, just to V on this side. And that will give you another sided calculus, which is entirely natural to have as well. It's just the opposite to the usual choice. Well, why not? And if you take, well, I'm going to use lambda for the exterior algebra just on the V's, given by the braiding on the V's and the cells. This lambda will just be this braided exterior algebra on them. So we can define omega PQ is equal to lambda P tensor B tensor lambda Q. And this will be a star differential calculus. Well, it turns out that the usual star operations work, but if you remember from this map here, where you get this order reversal, you get the same thing here. So if you star one of these things, you get something with the Q goes over here, the P goes over here, and you basically get this map doing, which does the reverse, and you define D just to be the sum of this operation plus that operation, and it gives this D plus D bar.
What is omega again?
This
Okay.
is the Morey-Cartan formed to the invariant, well, at least that's one way of looking at it. It is just a derivative map. So a Z in here would actually be interpreted as D bar Z. So if I apply this to some F in here, I would get something times D bar Z, and that Z would be what ended up in here. So a Z in here is a D bar Z. A Z on the other side is a DZ, curly DZ.
But then, so what is V then again?
V
comes from
is, so V is, well, just the linear functions on the plane really, Z and Z bar span V.
basically, so this is the, okay, so this B plus tensor V is your omega 0, 1. And it's just the usual present. This somehow it's a free module, and this is like the tangent space is V. Yeah. And how is omega from B plus to V
Is just
is the difference? How is it defined?
B plus is just a quotient preserving degree on the tensor algebra on V. So it has a well-defined projection to first order parts, which is just take the V to the power 1 bit.
So then it looks very much like differential calculus construction over a Hopf algebra. And this can also be interpreted.
Yeah.
Okay, nice, thank you.
Sorry, a follow-up question. So this B plus is a braided Hopf algebra, not a Hopf algebra. So then what is a differential calculus over a braided Hopf algebra? I don't know the definition.
It's got various rules, which I guess only make sense in a braided context about this, because all of these constructions are actually morphisms in the category, all of these things will, for example, commute with the braiding. So if you've got a braid here and a differential here, you can just pull the differential through the braid and so on. So because of that idea that all of these differential operators are morphisms, they just commute with all the braidings, and you then just write out diagrams for everything, really.
Mm-hmm. And then this will be a covariant calculus even in this braided sense, or? Okay.
Yes. Yes, because all of these operations are co-module mapped. So we get some, so these braidings will give us relations. For example, we've got Z star, dz is equal to Q, dz times Z star plus Q squared minus 1 dz times the dz star times Z. And that you can recognize that as coming from that braiding up layer. And then, so this is a relation in the 1-0 calculus, and to get the relation in the 0-1 calculus, we just star everything in sight, remembering that the curly Ds need to be also changed to curly D bars, and the order of everything has to be reversed. So one of these is the usual calculus. It's got a conjugate pair, and the star operation just maps from one to the other. So we've doubled the calculus up. Now I need to say a bit about inner products. So one natural way to get an inner product here is to choose a co-module map from V tensor V to C. Now, if you remember, we had a calculus which was V tensor V, and the other, that's the omega 0-1 calculus. This tensor product, the omega 1-0 calculus. And now we apply eta and just do multiplication, multiplication. And that is then going to give us an inner product, which in this case will go from omega 0-1 tensor omega 1-0 to B. Now, so this will basically automatically give you a B bimodule map. Now, at this stage, I need to remind you that multiplication of tensor products, if we have B tensor A, is given in the braided sense, which is you apply a braiding here, and then you've got two elements of B, you multiply them, two elements of A, you multiply them. So you have to sort of use this whenever you're asking all these things bimodule maps, because you need braided operations to put everything in the right order. But it works. What doesn't work is that this does not descend to tensor product over B. It would have if we hadn't inconveniently had to centrally extend the operation. But as I said, to get a braided place in the first place, we had to do a central extension. So, but anyway, it doesn't give a tensor product over B there. We'll come back to this little problem in a moment. So now, so on these calculi, well, so look, basically, I can use the open star map, which is a nice map in the calculus. to say that this is a Hermitian inner product. The rules for being a standard complex inner product and the complex conjugates that are in there are basically all to do with the fact that a complex inner product is really from V tensor conjugate V. So this is a Hermitian inner product. Now, how can I give the rules for an inner product like this to be preserved by a connection? So let's have, I'm conscious of the time here. I'm going to have to just assume that I can say connections. Okay, so if we have a connection here, this is a left connection, then I do an inner product here. I now want to do the same thing on here, but I have to use a right connection on here, do an inner product, and that's equal to what happens if I just take the inner product and then apply D to it. Now, because this is a conjugate, there is a very natural definition of what if I have a left derivative on E, I've got a very natural definition of a right derivative on E bar, which is just given by this operation here. So well, I need to, if I didn't have a conjugate but still kept this thing, I mean, you can produce other definitions by using bimodular covariant derivatives. You just have to think slightly more about it. So it's not particularly a problem. But anyway, there are nice definitions about what it means for a connection to preserve the inner products. And so given a D bar connection on E, then there is a Chern construction that says basically given any D bar connection on E, vanishing hot curvature, which just means D bar E from E to omega 0, 1 tensor E for an A module, then basically says that you can to get a connection with the conjugate forms on this, so that if you were to define, so if you were to direct some these two bits together, you get a connection with which has got values actually in just one form, which preserves the inner product. So that's the Chern construction, which I'm really not going to have time to say, but the proof is actually quite simple if you use my favorite things, which is matrices of Christoffel symbols. And basically, you can do this, and well, let's give an example of an inner product where eta is taken to be the Q epsilon tensor. Okay, I'm actually going to quote the inner product not conjugated. No, I am going to do it conjugated. So if we look at the inner product, and this is going to be on omega 0, 1 tensor, omega 0, 1 bar, doesn't matter, you can just move these into each other by using star operations. You get these values coming out of it, and you get, and the other two values are 0. And this is a connection which does not descend, but it has, but it basically has a metric preserving connection. for which all of these things are nabla of all of these D's of Z's or Z star are equal to 0. So that's really, in some senses, quite a boring connection, but hey, it satisfies all the rules. Now, but it doesn't descend. Now, can we fix this by making something which actually descends the tensor product over A? Well, yes, we can have a different inner product which descends the tensor product over A. But there is a price to be paid, and that price to be paid is we actually get a line bundle. So, let's take this inner product. Now, delta will be something I'll talk about in a moment. So this is going to be a linear, not Hermitian inner product. Well, as I say, you can shift it around from omega 1, 0 tensor omega 1, 0 to, well, there's going to be a line bundle in here, because what I want to do is I want to ask what is the condition for this descend to a tensor product over B. And it turns out that the condition is that where V is either Z or Z star is that. And this gives you a condition, well, this basically gives you a line bundle which is based on the grading of the quotiented tensor algebra B plus. So it's quite a simple line bundle, but nonetheless, you want it to descend, you have to have that. Now, so in order to finish this off in this diagram that I had over here, it just remains to say that that is now going to be an L over here, a line bundle, and this now has to be a connection on L. So in this case, there is a terribly boring connection on L for which all of this works, which is just that the derivative of L is equal to 0, and the same covariant derivatives as before actually work. So I'm sorry that things got a bit squashed at the end, but I think I'd probably better stop now.
Questions from the audience? Or?
I think you just have to define it, unfortunately. Yeah. As in knots and links, as in having a braid diagram angle like that, you mean? It's not a usual thing to do, but I mean, certainly, in principle, it could be done. I'm not quite sure what all the consequences of it will be. I mean, you get the reverse, if you shift the braiding over here, you get the reverse braiding and so on. So modulo having the opposite braidings on one side to the other side, and then you'd have to have evaluation maps between all. So it's effectively a dual construction. You'd need to be able to dual objects over here, reverse braidings, and in that case, you could pair them and you need to have a co-evaluation map at the top as well. So I think that, yeah, I think to that extent, it makes sense, yes. But the diagrams don't really work very well for zero lines.
Yeah, maybe coming back to your first blackboard, there was this finite set of points, and you were saying that if you want a star calculus on this finite set, you need arrows that go one way, but also the other way around. And then you mentioned that, okay, what you want to do is like just take one of these, yeah, and not both. And I'm kind of failing to see how this appeared in the talk. Can you explain a bit?
The one-way arrows would be the omega 01 or the other bit of the calculus. This can all be done for groups as well. There's a bit on that in the paper. Mm-hmm. So in that case, you would then want to say, does it make sense just to take connections on the omega 1 part, which are metric preserving? And the answer is sort of yes, because you can use a Chern construction on it. And this goes back to a very annoying bit of numerical analysis. When I was an undergraduate, we had to program sort of a weather forecast over the North Atlantic, just into a finite lattice model, and I ended up with 1,000-mile-an-hour winds and things like that in the Atlantic. And that is because the lattice models don't have any conservation laws, because so there was a long time ago, I read a proposal to produce sensible numerical schemes involving non-commutative geometry, because if you've got finite lattices, you have an exact calculus, only it's not commutative. And so you can have conservation laws in it, which actually work. But the annoying bit of this was that to have a star calculus, you have to double it up. And you do not have these doubled up calculi in your weather models. So trying to look at this all is rather belated now, because they've got methods now of coding serious conservation laws into finite element rules. And how did I get sidetracked into a weather forecast? Anyway, sorry.
Yeah, but is there some way to see, for example, this central extension that you did for the OQ-SU11? Can I also see this in the graph picture, in the finite set picture, or is this really a different picture that I shouldn't have in mind?
We didn't make a braided category description of that. However, I suspect that you could, because what we did was we just very artificially had the E pluses and E minuses going in different directions, and we had to introduce an exchange law. Well, in fact, that's quite natural for the integers. You don't have to introduce it. It just naturally has the exchange law because it's a nice abelian group. I think it probably does have a braided picture, which might be slightly more natural in the way we did it, but it's the same Chern construction behind it. It's just not the same, at the moment, not the same braided beginning.
Okay, thank you.
Other questions or online questions? Anybody just unmute yourself?
I think eventually it is, because that's built into this eta element. And if it had not been for the central extension, this simpler choice over there would in fact have descended to the tensor product over A. So So yes, and the other thing is that this omega 10 calculus gives you a delta. The other one would give you a delta inverse. So if you actually had this on the full omega 1 calculus, it would actually, the inner product would actually have values in a direct sum of a line bundle and its dual.
This somehow in the larger space, so you can still compose this to get an actual inner product. As in, you can compose the metric with. I'm thinking in the quantum group, quantum homogeneous space case, where you have these inner products, then you compose them with the higher, and then you get a genuine. Then you get an inner product. You go from metric to an inner product by composing with the state. But I guess you can still do this here, even though you land in a line bundle.
Well, if you compose with the state, you'll actually get a number valued inner product, which so it's not corresponding to a Riemannian inner product, which would have a but yes, it's certainly possible to get a sort of a numerical valued inner product.
Yeah, and then you can take a Hilbert space.
Yeah.
And what about a Hodge map for these calculi?
No idea.
But do you have some duality for the just duality?
Yes, I imagine everything will work because there is a braided picture of everything apart from that little problem of having a delta inverse on there. That inverse is an artificial not braided category construction, but everything else just lies inside braided category. Yes, braided Hodge constructions probably. Yes, but the metrics will again probably not descend. Actually, I also cheated very slightly. There is another metric which you can construct, which has got actual algebra valued as opposed to number valued entries, but it's degenerate, so it's not a very nice metric. But it does descend to tensor product over A. It's just pretty awful. Okay.
October, the first Tuesday of October, and it will be our own Thomas Faber, his inaugural lecture in Prague. So hopefully we will see you all there.